So let's look at the very last topic in Unit 1, and it's a very important topic. It's like one of the main concepts in calculus, and that is looking at average rate of change. Well, we'll start with average rate of change. So average rate of change is something that we've been doing since Math 1. All it is the slope of a line. Now, we get a little bit more sophisticated in pre-calculus, and we said, well, you could find the slope of the secant line. And a secant line is just anything that, a line that goes through a graph on 2 points. Okay? So and that's going to be really important that you remember average rate of change, that means the slope of the secant line. Okay, and you're going to want to pause and copy this down. Okay, so slope, just like we've always found. Okay, so back of your head, I want you to think average rate of change, slope of the secant line. That's what I've been doing since middle school. Okay, so what does it tell us? Well, it tells us the behavior of a function over an interval. Okay, we can tell if the function is increasing or decreasing by just looking at the slope. And then we can tell, is it going quickly or slowly? Again, looking at the slope. Or is it constant? Okay, so we like average rate of change. Okay, now there's another thing that's called average velocity. And we are going to be looking a lot at average velocity. And this is another thing I want you to put in your brain, that average velocity, because we're going to see there's a thing called instantaneous velocity. And I want you to go, okay, average velocity is just total distance over total time. That's all it is. And I want you to think about that you could have something moving along some path, and if you're finding its average velocity, you're just finding the slope of the secant line. Okay, again, that's going to be really important. Okay, so you'll want to pause, write that down. Okay, now we've got something different. Instantaneous rate of change. And that would be the slope of a tangent line. And we went over that in Unit 0. So instead of us knowing what's happening over the average rate over a distance, so if I told you that I took 2 hours to drive to Reno, and let's pretend Reno was 100 miles away, then you could go, okay, well, on average, you went 50 miles an hour. But that only tells you what I did on average over the entire interval. Not very helpful. Instantaneous rate, maybe you want to know, okay, how fast were you traveling over Spooner Summit? And you want to look at a speedometer. And you're looking at your speedometer, and you can get that exact rate that you're traveling right at a point. Okay, so I want you to be thinking back to Unit 0. Okay, so if I want to find the instantaneous rate of change, I'm talking about some point right on the graph. And we would just find the equation of that tangent line. And I believe back in Unit 0, we just sort of estimated it. We had some graph paper, and then we estimated what the slope was. Well, what we can do is we can just find another line that's parallel to the tangent line. So if we find something parallel, well, then we could get its 2 endpoints there, and we could calculate the average rate of change. And since the lines are parallel, the average rate of change would have to be equal to the instantaneous rate of change. Well, that's pretty cool. Okay, and we call the slope of the tangent the instantaneous rate of change. Okay, so remember, slope of the secant, average rate of change. Slope of the tangent, instantaneous rate of change. Okay, so now let's look at limits. So what a limit says is that, say you have 2 points, and I want the tangent at this particular point right here. Let me make sure that's in my notes here. And so what I do is I just get another point and I make a tangent. Well, that tangent, here, let me make this on a different piece of paper so that you guys can see what's happening. Okay, so let's say that I want the slope at that point right there. So I'm going to pick a point down here, and I'm going to call that point x1. And I'm going to pick a second point, and I'm going to call that point x2. Okay, so if I could just find the slope of that right there, well, I could use it to estimate that, but how about if I move this a little bit closer? So I move x2 a little bit closer to x1, okay, and then I'm going to get a different tangent line. And then I move it a little bit closer. And I keep moving it closer and closer and closer until, and actually let me show you one that maybe shows it more dramatically. Okay, so let's say I'm here and I'm here. Okay, well, that's my estimate of that point right there. Not very good. So I move it a little bit closer. And then I get a new tangent line. Still not very good because I can tell that that tangent line's going that way. So I move a little bit closer. It's a little bit better at estimating. I move it a little bit closer. Ooh, it's getting a lot better at estimating that tangent line. Well, what if I move it so close that I move it infinitesimally close so that this distance between here and here becomes 0? Okay, so that's what I'm thinking of doing. Okay, so back to our notes here. So I'm going to say as x2 gets closer to x1, the secant line starts to approach the tangent line. And if we call that distance between these two guys here, if we call it h, then consider it kind of like a limit. So the points on the secant line, instead of x1, y1, x2, y2, we'll call them x, f of x, and x plus h, f of x plus h. Okay, so I want you to really think about how does that work? In your mind, think about where h is and where the coordinates of those 2 points are. Okay, so here's what it's going to look like. So here's x1 and x2. We said that the distance between those two was h. So I could say that this is x and this is x plus h. This point right here is f of x. This point right here is f of x plus h. Okay, and again, this is blown up right here, but I want you to think about this as super, super small. So we're going to allow h, that distance between these 2 points, to go to 0. Okay. So there's the slope of the secant line. And I just replaced x1 and x2 with h. Okay, here's where that limit's going to come in. As h gets smaller and smaller, infinitesimally close to 0, the slope of the secant line is actually going to turn into the slope of the tangent line. Again, you'll need to pause to get that all in. Aha! Look at that. That is way cool. That we could just take a limit of that as h approaches 0, and we'll be able to get the slope of the tangent line. Super important formula. Okay, and then let's look at instantaneous velocity. And before calculus, we could never calculate it. Okay, that's what's on the speedometer. And instantaneous velocity is just slope of the tangent line. Okay, more on that coming up later. Okay, so I know I went through those quickly and you had to pause the video, but it's really important. This is like thinking homework, that you have to really think about it, draw pictures, make sure you understand, like conceptually, what's happening, because this is a big, huge topic in calculus. Okie dokie. See you later.